Hello. In this presentation, we're going to try to answer the following question. How many primes are there of the form 4k plus 3, where k is a natural number? Here we have an answer. We know the answer to be there are infinitely many. Our quest is to prove this. So let's begin. Our proof is 1 by contradiction. It's a reductio ad absurdum proof. So we begin by supposing there were finitely many. So suppose there were finitely many. So say that there are n of them. And here n will be a positive integer greater than 1. Okay, so let's make a list. Let P1 equal 3, which is the first of such primes, happens when k is 0. P2, 7, which happens when k is 1. P3, 11, which happens when k is 2. And so on up to Pn. Which will be our last prime. Now let's make the observation that in this list, P1 is less than P2 is less than P3, and so on up until Pn minus 1 being less than Pn. Now let's define an integer. So let m be the following integer: 4 times the product of P2, P3 all the way up to Pn plus 3. So P1, P2. I'm going to start my product at P2, P3 all the way up to Pn plus 3. Let's immediately observe that m happens to have the form 4 times an integer plus 3. But it is not 1. Let's make that observation right away. It's not 2 either. So m is an integer actually greater than 2. So it's not 1, it's not 2. It's greater than both of those. So, question. Is m prime? Answer, no. So, m cannot be prime. Cannot be prime because m is of the form 4 times an integer plus 3, but it is greater than each of the primes of that form we have in our list. we're assuming that this list contains all the primes of the form 4k plus 3. This integer, which is of the same form, is greater than each of those primes. So it cannot be a prime by our assumption. So m cannot be prime because m is greater than each of our primes of the form 4 times an integer plus 3. Okay, so now we would like to identify what primes can be factors of m. That's our next goal. So if m is not prime, then we would like to find out what prime divisors does it have. So does the 3 divide m? Is 3 a prime divisor of m? So does 3 divide m? Answer is no. It cannot. Because if you had m were a multiple of 3, that would imply, but if we take m as a multiple of 3 and subtract 3 from it, the answer is still a multiple of 3. But that would imply that 4 times the product, p2 all the way to pn, would have to be a multiple of 3. So no, because if 3 were to divide m, then 3 would have to divide the product, 4 p2 all the way up to pn. But this cannot happen. This is impossible. 3 dividing this product, notice that none of these primes is 3 because this is an increasing sequence. So 3 does not divide 4, 3 doesn't divide any of the primes, therefore 3 doesn't divide their product. So, which is impossible. So let's ask, can any other of the primes besides 3 in this list divide m? So does pj divide m, where j equals 2 or 3 or all the way up to n? Here the answer is negative. No, that cannot happen. And that's because if we had that pj divides m, so you would have pj as a factor of m and also as a factor of 4 times p2, p3 all the way to pn. That would imply that pj would have to divide 3. So if pj were to divide m, then pj would have to divide 3. But remember, the prime pj for j equals 2 up to n is actually greater than 3, which is, so this is impossible. Okay, so now we have to question. So if none of these primes can divide m, could the prime factorization of m consist of other types of primes? The answer is yes, it would have to be primes of the form 4k plus 1, which are the rest of the primes. We conclude that the prime factorization of m must consist exclusively of primes of the form 4k plus 1, because none of our primes of the form 4k plus 3 can divide m. That means the prime factorization of m can only have these types of primes. Unfortunately, that's impossible. This is impossible. And the reason for this is when you take products of integers of the form 4k plus 1, the answer to those products is still of that same form. So observe, if we were to multiply, two integers of the form 4k plus 1, so let's say 4k1 plus 1 times 4k2 plus 1, the answer would be 16k1 k2 plus 4k1 plus 4k2 plus 1. Now we get to factor the common factor in the first three terms, which is 4 times any integer, whatever is left, plus 1. So whenever I multiply integers of the form 4k plus 1, our answer will be another integer of the form 4k plus 1, not of our form, which is 4 times an integer plus 3. So now we have run out of options. Our integer m cannot be prime, but now our integer m cannot be composite either. You could assert that this led us to conclude that m has no prime factorization. So we conclude m has no prime factorization. In spite of the fact that m is greater than 1. This is a contradiction to the fundamental theorem of arithmetic. The fundamental theorem of arithmetic says that any integer greater than 1 will have a prime factorization. The m we defined in this proof under the assumption that there were finally many primes of the form 4k plus 3 failed to meet this condition. So we must reject our assumption. So we must reject the possibility that there are finitely many primes of the form 4k plus 3. Therefore, there exist infinitely many such primes. And that concludes our presentation. Thank you for watching.